On the 24th of January, 1986, at 1759 hours Universal Time, a small aluminum and graphite spacecraft, 825 kilograms in weight, roughly the size of a small car, passed within 81,500 kilometers of the cloud tops of a pale blue-green planet. Its name was Voyager 2. It was moving at 19.5 kilometers per second, about 43,500 miles per hour, and it had been traveling for 8.5 years to reach this moment. For the next 5.5 hours, its cameras and instruments turned toward the seventh planet from the Sun, and then it kept going. That night is the only night in the history of the human species when a machine has flown close to Uranus. Everything we have ever seen up close of that planet, every cloud band, every crescent moon, every ring, comes from those few hours. No spacecraft has returned since, and no spacecraft is expected to return before the year 2045. We are here tonight to walk, very slowly, through what Voyager 2 saw on that single night, and through everything the telescopes on Earth have added in the 4 decades since. Let us begin. Uranus is the 7th planet from the Sun. It is roughly 19 astronomical units out, about 2.87 billion kilometers, or 1.78 billion miles. Sunlight there is about 1/370th of what falls on the Earth. It takes light from the Sun 2 hours and 40 minutes to reach it. Its equator is 50,724 kilometers across, about 31,763 miles. That is roughly 4 times the diameter of the Earth. You could fit 63 Earths inside its volume. But its total mass is only 14.5 Earth masses. The reason is simple. Uranus is not made of rock. It is not really made of gas either, not the way Jupiter and Saturn are. Uranus and its neighbor Neptune belong to a third category of planet. Astronomers call them ice giants. Under the pale blue clouds, most of the planet is a hot, dense fluid of water, ammonia, and methane, compressed to pressures we still cannot fully reproduce in any laboratory on Earth. Its year lasts 84 Earth years. It has 28 known moons. It has 13 named rings. And its axis of rotation is tipped over almost completely on its side, at an angle of 97.77 degrees to the plane of its orbit. Uranus does not spin like a top. It rolls. For half of its long year, for 42 Earth years, one pole is turned toward the Sun and bathed in continuous daylight. For the other 42 years, that same pole is turned away and locked in continuous darkness. No other planet in the solar system behaves this way, and this is where the story really begins. Because on that January night in 1986, when Voyager 2 came within 81,000 kilometers of the cloud tops, Uranus was almost exactly at the wrong moment of its long year for a visitor. The southern pole was pointing directly at the Sun. The southern pole was also pointing directly at Voyager 2. The spacecraft did not see the equator, or the storms, or the seasonal cycle. It saw a smooth, pale blue-green disk, almost featureless, like a marble held up to a lamp. And for many years afterward, that image is what most people thought Uranus looked like, the most boring planet in the solar system. That impression was wrong. But we will come back to that. First, let us look at where Voyager 2 was standing when it took the photograph. The spacecraft was launched on the 20th of August, 1977, from Cape Canaveral in Florida on a Titan IIIe Centaur rocket. Its twin, Voyager 1, launched 16 days later on a faster trajectory toward Jupiter and Saturn. Voyager 2 took the long path, the grand tour. Jupiter in July 1979, Saturn in August 1981. Then a 5-year cruise, silent, coasting through a part of the solar system no spacecraft had ever entered. Uranus in January 1986. Neptune in August 1989, and after that, out into interstellar space, where it is still traveling today. But for those 5.5 hours in January 1986, Everything the mission had built toward focused on one blue planet. The signal from the spacecraft, moving at the speed of light, took 2 hours and 40 minutes to reach the Earth. That signal was picked up by 3 enormous dishes, one in the Mojave Desert of California at Goldstone, one outside Canberra in Australia, and one outside Madrid in Spain. Together, they are called the Deep Space Network. The 70-meter antennas at Goldstone and Canberra were the primary receivers that night. At the Jet Propulsion Laboratory in Pasadena, in a plain, brightly lit room with rows of monitors and stacks of paper printouts, the flight team watched the first close pictures of Uranus arrive. The image data came in slowly, one line at a time. Because Uranus is so far from the Sun, the light is thin there, and the cameras had to take long exposures. Because Voyager 2 was moving so quickly past the planet, those long exposures had to be taken while the entire spacecraft slowly rotated, tracking the target, a maneuver the flight team had rehearsed for years. If it had failed, the pictures would have been blurred beyond use. It did not fail. Voyager 2 returned more than 7,000 images from Uranus and its moons. It also carried instruments to measure fields and particles and radio waves, a magnetometer, an ultraviolet spectrometer, a photopolarimeter, an infrared radiometer, a plasma detector, a cosmic ray detector, and a radio science experiment which used the spacecraft's own transmitter to probe the atmosphere and the rings by watching how the signal bent as Voyager 2 passed behind them from Earth's point of view. In the space of one long day, Voyager 2 rewrote the textbook on Uranus. Before that night, we knew of 5 moons around the planet: Titania, Oberon, Umbriel, Ariel, Miranda. By the time Voyager 2 passed behind Uranus, we knew of 16. Voyager 2 imaged 11 new moons, small, dark, close in to the planet: Puck, Portia, Juliet, Belinda, Cressida, Desdemona, Bianca, Cordelia, Ophelia, Rosalind, and one more, later named Perdita. 10 of those were recognized in the days immediately after the flyby. The 11th, Perdita, was quietly hidden in an old Voyager frame the whole time, and was only picked out again in 1999. Before that night, we knew of 9 rings around the planet. They had been discovered in 1977 from an airplane flying over the Indian Ocean, in a way we will describe later in this film. By the time Voyager 2 passed behind Uranus, we knew of 11. Voyager 2 discovered 2 new rings, and it photographed all of them, edge-on and backlit by the sun, the first time in history any spacecraft had seen the ring system of Uranus at all. Before that night, we suspected Uranus had a magnetic field. We did not know its shape. Voyager 2 discovered a magnetic field that is deeply strange. The center of that field is not at the center of the planet. It is offset by about a third of the Uranian radius, roughly 8,000 kilometers, from the geometric center. The magnetic axis is tilted by 58.5 degrees away from the rotation axis. By comparison, the Earth's magnetic field is offset from the Earth's center by only about 500 kilometers, and the tilt is only about 11 degrees. The magnetosphere of Uranus is not a quiet, symmetric bubble. It is a lopsided, tumbling shape, opening and closing as the planet rotates once every 17 hours and 14 minutes. Even now, 40 years later, no other planet we know of behaves this way. And before that night, Uranus had never given up any of its internal heat. Voyager 2 measured how much heat the planet was radiating into space. The number was tiny. For every unit of sunlight the planet absorbs, Uranus radiates back only about 1.06. For comparison, Neptune radiates back 2.6. Jupiter and Saturn each radiate more than twice what they absorb. Uranus does not. Almost all of the warmth in its clouds is delivered by the distant sun. Whatever internal heat the planet had 4.5 billion years ago seems to be, for reasons we still do not fully understand, trapped somewhere deep inside. That is a great deal to learn in a single night. But there is something we have to say plainly, because it is part of the story. On the 28th of January, 1986, 4 days after the closest approach, the Space Shuttle Challenger broke apart 73 seconds after launch from Cape Canaveral. 7 astronauts were killed. For weeks afterward, the news coverage of the Uranus flyby, which had been carefully planned to fill front pages and evening broadcasts, was almost invisible. The scientists at the Jet Propulsion Laboratory kept working. The images kept coming down. The papers were written. The maps were drawn. But the wider world barely noticed that we had, for the first and only time in our history, visited the 7th planet. Voyager 2 is still transmitting. At the time of this recording, it is more than 20 billion kilometers away, about 21 billion, in the direction of the constellation Pavo, and its signal, sent at about 22 watts, takes nearly 19 hours to reach the Earth. It will lose the last of its power sometime around the year 2030. Long before then, it will have stopped talking. And still, even after Voyager 2 is silent, even after the last spacecraft that has ever seen Uranus from close up has gone quiet forever, we will be waiting. The next spacecraft to visit Uranus does not yet exist. The mission that is being planned, the Uranus Orbiter and Probe, is expected to launch sometime in the early 2030s. It will not arrive until the mid-2040s, which means that, in a rough sense, everyone alive today who is old enough to hear this sentence will experience the entire arc of human close-up knowledge of Uranus as one night in January 1986 and one long, long wait afterward. Tonight, we are going to spend this long wait together. We will go back to 1781 and stand in a small garden in the city of Bath, in the west of England, and watch an amateur astronomer notice a star that will not stay still. We will follow the discovery of the rings from a converted cargo plane flying at 40,000 feet. We will look, carefully, at the 5 large moons of Uranus and stand at the edge of the 20-kilometer cliff on Miranda that Voyager 2 photographed from just 29,000 kilometers away. We will trace the magnetic field down into the planet and into the strange kind of ice that physicists have only recently learned exists. We will watch the planet wake up in 2007, when the seasons finally turned. And in the end, we will return to that single night in January 1986 and to the small spacecraft that is still, somewhere far past Neptune, carrying its cameras through the dark. For now, let us begin with the man who was not looking for a planet at all. The city of Bath, in the west of England, is a small city. Its buildings are made mostly of a soft, honey-colored stone quarried from the hills around it that has been used since the Romans arrived there almost 2,000 years ago to bathe in the hot springs. In the year 1781, the city was in a quiet moment of its history. The great social season, when wealthy families from London came down to drink the mineral waters and attend concerts, was still going on, but a little less brightly than it had a generation before. And on New King Street, on the north side of the city, in a small terraced house at number 19, a 42-year-old man named William Herschel was preparing to look through his telescope. He was not a professional astronomer. He was an oboist and an organist. He had been born in Hanover, in what is now Germany, in November of 1738, and had come to England as a young man to make his living as a musician. He conducted concerts in the Octagon Chapel and in the assembly rooms of Bath. He composed symphonies. His younger sister, Caroline Herschel, had come from Hanover to join him a decade earlier and had trained herself as a soprano to sing in his concerts. But in his private hours, William Herschel had begun to build telescopes. He was not the first amateur to do this, and he was not the first to grind his own mirrors. But he did it with an extraordinary patience. He would sometimes sit at the polishing tools for 16 hours at a time, refusing to leave the workshop even to eat, while Caroline placed food into his mouth so that the mirror would not cool and warp under a temperature change. By the spring of 1781, he had built himself a Newtonian reflecting telescope with a primary mirror about 6.2 inches across, about 15.5 centimeters, with a focal length of a little under 7 feet. By the standards of the day, it was a very good instrument. He was using it to carry out a survey of the sky. He was going, methodically, star by star, working his way across small strips of the celestial sphere, measuring the brightness and the color and the exact position of every point of light he could see, looking especially for what he called double stars, pairs of stars that appeared close together in the eyepiece. Some of these pairs are truly close together in space, orbiting each other. Some of them only happen to line up. Herschel wanted to catalog as many of them as he could. On the evening of the 13th of March, 1781, he was working his way through a small region of the sky in the constellation Taurus, close to the boundary with Gemini. He noted, in a corner of his eyepiece, one star that did not look quite right. It was slightly larger than the stars around it. Not brighter, larger. A tiny visible disk instead of a point. He wrote in his observing journal that night, "In the quartile near Zeta Tauri, the lowest of two is a curious, either nebulous star or perhaps a comet." He did not, in that first note, use the word planet. He suspected a comet. Over the following nights, he watched the small object move. Its motion was slow, much slower than the motion of a nearby comet would be, and it kept its small disk. He sent his measurements to Neville Maskelyne, the Astronomer Royal at Greenwich. Maskelyne examined them. He wrote back that he could not decide whether the object was a comet or a new planet. The word had been used, cautiously, for the first time. Over the next 2 years, mathematicians across Europe worked to compute an orbit for the strange body. If it was a comet, the orbit would be highly elongated and would take it out of the solar system, or plunge it in toward the sun. If it was a planet, the orbit would be nearly a circle. The most careful of these calculations was done in St. Petersburg by the Swedish-born mathematician Anders Johann Lexell. By 1783, Lexell had shown that the orbit fit almost exactly onto a circle, of radius about 19 times the distance from the Earth to the Sun. The object was a planet. It was almost twice as far from the Sun as Saturn, the outermost planet then known. It had been sitting in the same orbit, unremarked, for the entire recorded history of astronomy. Every ancient astronomer, every medieval catalogue, every Copernican or Keplerian diagram had drawn the solar system with 6 planets, the Earth and its 5 visible neighbors. That number had held since antiquity. In 1781, the number changed. For the first time in the history of the human species, a new planet had entered the map. And it had been found not by a court astronomer, but by an amateur musician working out of his back garden in a small English city. King George III was informed. He was extremely pleased. He granted William Herschel a royal pension of £200 per year, enough to live on comfortably, and appointed him King's personal astronomer, on the condition that Herschel moved to the neighborhood of Windsor, where the king could occasionally look through the telescope himself. Herschel accepted. The house at 19 New King Street was closed up, and the family moved. The pension freed him from music entirely. For the rest of his life, he built telescopes and observed the sky. Caroline came with him and became his official assistant, paid £50 per year by the Crown, the first woman in England to be paid a salary for scientific work. She also began to make her own discoveries. Between 1786 and 1797, she found 8 comets and was awarded a gold medal by the Royal Astronomical Society for her work. But that came later. In the immediate aftermath of the discovery in 1781, there was one very awkward question. What was the new planet to be called? Herschel himself proposed a name. He wanted to call it Georgium Sidus, the Star of George, after the king who had rewarded him. The name was politically appealing in Britain. It was not appealing anywhere else. French astronomers in particular refused to use it. Some astronomers began to call the planet simply Herschel after its discoverer. But the eventual name came from the German astronomer Johann Elert Bode at the Berlin Observatory, who suggested in early 1782 that the planet should be named after a figure from ancient Greek mythology, in keeping with the tradition of the other planets: Mercury, Venus, Mars, Jupiter, Saturn. Bode proposed the name Uranus. Uranus, in the Greek tradition, is the personification of the sky. He is the father of Cronus, whom the Romans called Saturn, and the grandfather of Zeus, whom the Romans called Jupiter. Naming the seventh planet Uranus placed it, in mythology, as the ancestor of the two gas giants inside it. The name spread slowly. For most of the late 18th and early 19th centuries, both names, Georgium Sidus and Uranus, appeared in almanacs, and even in official British publications. The Nautical Almanac Office in London did not adopt Uranus as its standard until 1850, 69 years after the discovery. By then, William Herschel had been dead for almost 40 years. He had died in Slough, near Windsor, in August of 1822, at the age of 83. But before he died, he made two more discoveries about the planet he had found. On the 11th of January, 1787, 6 years after the discovery of Uranus, Herschel, now using a much larger reflecting telescope, 20 feet long, with a primary mirror nearly 19 inches across, noticed two faint points of light close to the planet. They moved with it, night after night. They were the two largest moons of Uranus. Herschel did not name them. His son, John Herschel, would give them their names 65 years later, drawing from the plays of William Shakespeare and the poetry of Alexander Pope, a naming convention which has been used for every Uranian moon discovered since. The larger of the two Herschel called number 1. We now call it Titania. The smaller he called number 2. We now call it Oberon. Titania is 1,578 kilometers across and is the largest moon of the Uranian system. Oberon is 1,523 kilometers across. Both are icy worlds with dark, cratered surfaces. We know this because Voyager 2 flew past them in January 1986. Before that, they were nothing more than points of light. Herschel also, later in his life, began the enormous construction of a much larger telescope, a mirror 4 feet across, mounted in a wooden framework 40 feet long. This 40-foot telescope, as it was called, was for a time the largest telescope on Earth. It never worked especially well. The mirror was too heavy to be easily maneuvered, and the mirror surface degraded quickly. But its skeleton stood outside Herschel's house in Slough for the rest of his life. The image of it, a sketch of the great wooden truss with figures on ladders working to align the mirror, became one of the first icons of large-scale astronomical instrumentation. More than a century later, when the great telescopes on Mount Wilson and Palomar and Mauna Kea and in orbit were being built, that sketch was still hanging on the walls of astronomers' offices. There is one more small detail about Bath that is worth mentioning tonight. The house at 19 New King Street still stands. It is now the Herschel Museum of Astronomy. Visitors can walk through the small ground-floor rooms where the family lived and rehearsed music, through the workshop in the basement where the mirrors were polished, and out into the small back garden. The paving stones of that garden are still, largely, the same paving stones that were there in the spring of 1781. That is the place. That is the exact spot on the surface of the Earth. From that small rectangle of stone, one evening in March, a musician looked into a telescope and doubled the size of the known solar system. Everything that we will look at for the rest of this film begins from there. Every image sent back by Voyager 2, every close-up of a moon, every ring found from an airplane, every measurement of a magnetic field, every plan for a mission that we are still slowly drawing up. All of it descends from a note in a small observing journal written in ink on a night in March of 1781. Curious, either nebulous star or perhaps a comet. The journal itself still exists. It is held in the archives of the Royal Astronomical Society in Piccadilly in central London. You can request to see it in a reading room under supervision. The pages are yellowed with age. The ink is a warm brown, faded and softened by 245 years of quiet drying in cardboard boxes. Herschel's handwriting is small and neat. The relevant entry occupies about 3 lines of a page. Above it and below it are other observations from the same evening, other stars, other pairs, other measurements, all recorded in the same tidy hand, without any special notation for the sentence that would, in retrospect, change the size of the known world. He did not know. He could not have known. He wrote the observation, closed the journal, folded up the eyepiece, went inside, and went to sleep. The 7th planet, meanwhile, continued its slow circuit around the Sun. It would take another 2 years of computation by mathematicians in 3 countries before the world caught up with what William Herschel had noticed one Tuesday evening in a small garden at the end of a long British winter. For a long time after Herschel found Uranus, nobody was quite sure what it was made of. It was too far away and too small in the eyepiece for the great refractors of the 19th century to show any surface features at all. It looked like a small, pale disk, almost featureless, almost a smaller version of Jupiter or Saturn. For the whole of the 1800s, and for much of the 1900s as well, astronomy simply called it a gas giant. 4 large planets out beyond the asteroid belt. Jupiter and Saturn, the giants. Uranus and Neptune, the smaller giants. All 4 presumed to be, in essence, the same kind of world. Great balls of hydrogen and helium wrapped around a small, rocky core. Only 2 things about Uranus really stood out. One was its color. It looked, in every telescope pointed at it, a pale, cold blue-green, the color of the sea when the sky is overcast. Saturn was straw yellow. Jupiter was pinkish tan. Uranus was blue. The second thing was the temperature. Uranus is far from the Sun. At its average distance of about 19 astronomical units, 2.87 billion kilometers, or 1.78 billion miles, sunlight is thin. The tops of the clouds are one of the coldest sustained temperatures in the solar system. The lowest measured temperature at the top of the atmosphere is about 49 kelvins. That is, minus 224 degrees Celsius, minus 371 Fahrenheit. Cold enough that if you could hold a jar of oxygen up to the clouds of Uranus, the oxygen inside would freeze solid. But this is where the trouble starts. Because Uranus is not just cold on the outside. Uranus, unlike its neighbors, appears to be very close to being cold on the inside as well. We know this because, in the 1970s, before Voyager 2 ever reached it, infrared telescopes could measure roughly how much heat energy the planet radiates back into space. Every planet with an atmosphere absorbs some fraction of the sunlight that reaches it, warms up, and then radiates a corresponding amount of infrared energy back out. If a planet has no internal heat of its own, the amount of energy it radiates should equal the amount it absorbs. If a planet has internal heat, from ongoing gravitational contraction, from the slow settling of heavier elements, from the decay of radioactive elements, it will radiate more than it absorbs. Jupiter radiates about twice as much energy as it absorbs. Saturn radiates about the same. Neptune, which we will meet properly in a later film, radiates about 2.5 times as much. Uranus radiates about 1.06 times as much. For all practical purposes, Uranus is in balance. Whatever heat is left over from its formation, 4.5 billion years ago, seems to be trapped somewhere down inside it, unable, for some reason, to leak out. That is the first great oddness of the planet. It is why, for decades, planetary scientists placed a small marker next to the name Uranus in every table of the outer solar system: the thermal anomaly. The second great oddness is what Voyager 2 discovered when it flew past in 1986. The average density of Uranus is 1.27 grams per cubic centimeter. Jupiter is 1.33. Saturn is 0.69, less than water. Neptune is 1.64. At first glance, 1.27 does not stand out. But the internal structure that is required to produce that density at the mass of Uranus cannot be simply hydrogen and helium in the way that Jupiter and Saturn are. Jupiter and Saturn, in the current picture, are enormous atmospheres of hydrogen and helium with a small rocky core at the very bottom, no more than a few percent of the total mass. Uranus and Neptune are different. Only the outer 20% or so, the atmosphere that we can see, is hydrogen and helium. The vast majority of the planet, everything under the visible clouds, is something else: water, ammonia, methane. Compressed at colossal pressure to depths of tens of thousands of kilometers. At the pressures and temperatures inside Uranus, water is not water in any familiar sense. It is not liquid water, like the water in a lake. It is not steam. It is not the clear, crystalline ice you find in a freezer. Deep inside the planet, water molecules are compressed to about 1,000,000 times the pressure at the Earth's surface, perhaps 100 gigapascals or more, and heated to thousands of degrees. Under those conditions, in laboratory experiments carried out only in the last few years, water enters a strange phase that physicists now call superionic ice. In superionic ice, the oxygen atoms lock themselves into a rigid, crystalline lattice, like a solid. But the hydrogen nuclei, the protons, tear themselves free from the oxygens and swim through that lattice, like a liquid. The result is a solid framework flooded with a mobile sea of positive charges, a material that is, at the same time, a crystal and an electrical conductor. This phase was first predicted from theoretical calculations in the 1980s. It was directly demonstrated in a laboratory experiment in the year 2018. A team led by Marius Millot, working at the Omega Laser Facility at the University of Rochester in New York State, fired an intense laser pulse at a small sample of pre-compressed water. For a few billionths of a second, the sample reached pressures and temperatures similar to what would be found several thousand kilometers below the top of the clouds of Uranus. Their measurements showed the electrical conductivity jumping suddenly upward, exactly as the superionic model predicted. The result was published in the journal Nature Physics in May of 2018. For the first time in history, a physical sample of the interior of Uranus, a tiny, brief, laser-heated speck of it, had existed in a room on the surface of the Earth. Below the superionic layer, deeper into the planet, the pressure and temperature keep climbing. Nobody is entirely sure what happens down there. Some models place a small, rocky core at the very center of Uranus, perhaps half an Earth mass, perhaps a full Earth mass, made of iron and silicates, wrapped in the deep, icy mantle. Other models suggest that the interior grades smoothly from icy fluid into rocky fluid, with no sharp boundary anywhere. We do not yet have the measurements to decide. The next spacecraft to arrive, the Uranus Orbiter and Probe, if it flies, will carry instruments that could finally distinguish between these possibilities. For now, all we can honestly say is that the inside of Uranus is a place we have never touched, and only briefly imitated in a room on Earth. The atmosphere above all of this is, by comparison, well understood. At the top, hydrogen molecules, H2, make up roughly 83% of the gas. Helium, the same element that fills party balloons, makes up about 15%. Both of these are the primordial materials of the early solar system, mostly unchanged since the planet formed. Then, at about 2.33%, comes methane, CH4. Methane is a modest fraction by mass, but it is exactly the right fraction to give the planet its color. Methane absorbs light strongly in the red and infrared parts of the spectrum. It scatters and transmits blue and green. When sunlight falls on Uranus, most of the red is drained out of it before the light gets back to us. What we see is what is left over. Blue-green, sometimes described in older textbooks as pale aquamarine. Recent, careful measurements, including a study led by Patrick Irwin of the University of Oxford, published in the monthly notices of the Royal Astronomical Society in 2024, have refined the true color of Uranus more precisely than ever before. It is not the almost pastel blue that a lot of old artistic renderings show. It is a deeper, richer, slightly greenish blue, closer to the color of a shallow tropical sea over a pale sand bottom. Neptune, in the same study, turned out not to be the vivid, deep blue of the classic Voyager 2 images either. The old Neptune images had been strongly color-enhanced. The two planets, when their true colors are shown side by side, are much more similar than we used to think. Both are, at heart, blue-green worlds. Neptune is only slightly deeper. Below the visible clouds, there are layers we have not yet directly seen. Models predict, going downward, a thin layer of methane clouds, then hydrogen sulfide clouds, the compound that smells like rotten eggs on Earth, then ammonia and ammonium sulfide clouds, then, much deeper, layers of water ice clouds. The presence of hydrogen sulfide in the upper atmosphere of Uranus was confirmed, from the ground, in 2018, using the Gemini North Telescope in Hawaii. If you could stand somewhere above the cloud tops of Uranus and open the visor of your helmet, you would probably not survive long enough to smell anything. But if you did, the last thing you would smell would be, very faintly, rotten eggs. There is one more measurement worth pausing on. Uranus has an escape velocity, the speed at which an object would have to be moving straight up to escape its gravity, of about 21.3 kilometers per second. That is a little less than half the escape velocity of Jupiter. It is only slightly less than that of Neptune. It is enough to hold on to hydrogen and helium, the two lightest elements in the periodic table, for the full 4.5 billion years of solar system history. Which means, in a sense, that the atmosphere of Uranus is one of the oldest surfaces we know of. The hydrogen molecule you would find at the top of its clouds tonight, if you could sample it, was almost certainly present at the top of its clouds when the first single-celled life appeared in the oceans of the Earth. Nothing on Earth is that old. Not the mountains, not the oceans, not the crust of the sea floor, which is constantly being remade, not the atmosphere we breathe. The blue-green haze of Uranus, at its top layer, is essentially untouched primordial gas, cold enough to freeze oxygen, old enough to have watched the solar system settle into its present shape. And, apart from a few hours of remote inspection by a single passing spacecraft, essentially untouched by anything we have ever built. That is the world Voyager 2 came to visit. Before we watch it arrive, we should understand one more thing. Something that makes Uranus stranger than anything else in the solar system. Something that Herschel could not have known, and Voyager 2 discovered by accident. The angle at which this whole vast planet is tilted. Before we go there, one last small note about the chemistry. The methane and hydrogen sulfide and ammonia that make up so much of the atmosphere of Uranus are all molecules that, on the Earth, are associated with life. Methane is produced on our world by rice paddies, by cattle, by anaerobic bacteria in wetlands, by natural gas fields. Hydrogen sulfide is what makes rotten eggs smell. Ammonia is what escapes from cleaning products under a kitchen sink. On the Earth, all three of these gases are, in various ways, the exhalations of living things, or the byproducts of chemistry that has been shaped by life over billions of years. On Uranus, none of that applies. The methane and the hydrogen sulfide and the ammonia have all been there since the formation of the solar system. They are not the exhalations of anything. They are simply the leftover primordial gases of a very old planet, cold enough that no chemistry has yet driven them anywhere. There is no life on Uranus. There is no evidence, in anything Voyager 2 or Hubble or James Webb have ever seen, of any process on Uranus that resembles biology. There is, In the coldness and the darkness and the slow permanence of the seventh planet, only the faint chemical echo of the very beginning. Every planet in the solar system is, to some degree, tilted. Nothing spins perfectly upright. The Earth is tilted at 23.44 degrees. That is the tilt that gives us the seasons, the winter and summer of the middle latitudes, the constant sun of the tropics, the 6-month days and 6-month nights near the poles. Jupiter is tilted at 3.13 degrees, almost nothing. Its poles are essentially aimed at right angles to its orbit, and it has almost no seasons at all. Mars is tilted at just over 25 degrees, remarkably close to the tilt of the Earth. Saturn is tilted at 26.73 degrees. Neptune, at the very edge of the solar system, is tilted at 28.32 degrees. Even Venus, which spins backwards, has an axis that is not far from vertical to its orbit. Its extreme value comes from spinning in the opposite direction, rather than from any large tilt. None of these numbers exceeds 30 degrees. Every major planet in the solar system, except one, has a tilt somewhere between 0 and about 30 degrees. Uranus is tilted at 97.77 degrees. That is more than 90 degrees, which means the planet is not merely tipped over. The planet has been rolled past vertical. If you were to draw the orbit of Uranus around the Sun, and then draw its rotation axis, the axis would be lying almost exactly in the plane of the orbit, pointing very slightly below it. The north pole of Uranus is not above the plane of its orbit. It is slightly below it. Uranus is spinning, in effect, upside down. There is no other planet like this. Uranus does not spin like a top. Uranus rolls. Imagine for a moment the solar system as a great flat disk, with the Sun at the center, and each planet moving in a wide circle around it. Imagine each planet as a small marble, spinning on its own axis as it goes. 6 of those marbles are close to being spun like tops, their axes pointing more or less straight out of the disk. One of them, the 7th, has been laid on its side. Its poles do not point out of the plane of the solar system. Its poles point along the plane of the solar system. And because Uranus takes 84 Earth years to complete one orbit around the Sun, this odd geometry produces the strangest annual cycle of any planet we know. Consider what happens at the north pole of Uranus. For part of the 84-year orbit, the part where the north pole is aimed toward the Sun, that pole receives continuous sunlight. The Sun does not rise or set. It sits nearly overhead, or slowly wanders in a small circle in the sky, day after day, for years and years. For 21 years, the North Pole is in continuous daylight, brightening slowly toward the moment of maximum tilt at the solstice. Then, for the next 21 years, the pole slowly turns away from the Sun. The Sun sinks lower in the sky, still visible, still shining continuously, but no longer directly overhead. Then comes the equinox. For a brief period, a few Earth years, on either side of it, Uranus is sideways to the Sun. Both hemispheres are lit. The Sun rises and sets across the sky in the normal way. There is something like a normal day and night cycle. And then the North Pole begins to turn away from the Sun completely. For the next 21 years, the pole is in continuous twilight, and then in continuous darkness. The Sun does not rise at all. Then, for the 21 years after that, the darkness deepens toward the winter solstice. At the coldest moment of the coldest part of the Uranian year, the North Pole of the planet has not seen the Sun in nearly 4 decades. Then, slowly, over another 21 years, the darkness lifts again. The pole turns back toward the Sun. The Sun rises for the first time in more than 40 years. The whole cycle takes 84 Earth years. Half of that time, 42 years, one pole is in some form of daylight. The other half, 42 years, that same pole is in some form of night. No other planet in the solar system has anything like this. On Uranus, the equator is not where the sun beats down the hardest. The equator, at solstice, is actually the coolest place on the planet. The pole, aimed straight at the sun, is where the light is most concentrated. The seasons at Uranus are not the seasons we know. They are seasons of geometry. Now, how does this happen? How can an entire planet, 4 times the diameter of the Earth, be lying on its side? The current best explanation is that sometime in the first few 100 million years after the formation of the solar system, Uranus was struck by something enormous. Simulations run in the past decade, most notably by Jacob Keck and colleagues at Durham University in England, published in the Astrophysical Journal in 2018 and refined since, have looked in detail at this question. They start with a model of a young Uranus, its axis still nearly upright. They then simulate a collision with a rocky body, somewhere between 1 and 3 Earth masses in size, arriving from just the right angle at just the right speed. The impact does not shatter the planet. The planet is too massive for that. Instead, the impact deposits an enormous amount of angular momentum into the outer layers of Uranus, enough to knock the planet's rotation axis nearly 90 degrees over its side. The simulations do more than just reproduce the tilt. They predict several other things about the planet that Voyager 2 found in 1986. They predict that a great deal of ice and rock would be flung into orbit around the young Uranus in the aftermath of the collision, material that would slowly settle into a disk and eventually form moons and rings. Uranus has, as we now know, a system of 28 moons and 13 named rings, most of them tightly organized in the plane of the planet's equator. That plane is, of course, itself tipped over by 97 degrees. The moons and the rings all go around Uranus, in effect, sideways. They do not orbit in the plane of the solar system. They orbit in the plane of the tipped-over equator of the tipped-over planet. This is exactly what the impact simulations predict. The moons and rings should have been assembled from post-impact debris, and that debris should have naturally settled into the new tilted equatorial plane, not the old, undisturbed one. The simulations also predict that a large impact should have disrupted the internal structure of the planet, perhaps stripping some of the outer envelope, perhaps trapping some of the impactor's mass deep in the interior, and that this disruption should show up as anomalies in the planet's magnetic field. We will come back to the magnetic field of Uranus in detail in a later part of this film. For now, it is enough to say that the magnetic field is one of the strangest in the solar system, offset from the center of the planet, tilted at an enormous angle to the rotation axis, and pulsing on and off with each 17-hour rotation. An old, undisturbed planet does not usually produce such a field. A planet that has been struck by something the size of a small world and then rebuilt in the ruins might. Not every scientist working on Uranus is fully satisfied with the single impact story. There are subtle problems. For example, if the tilt of the planet had been produced by a single collision, that collision would have almost certainly left the planet spinning much faster than we observe today. Uranus rotates on its axis once every 17¼ hours, a length of day that is quite ordinary for a gas giant. Some models therefore suggest that a series of smaller impacts over a longer time could have tipped the planet more gently, while also allowing time for its spin rate to relax. Other models suggest that a single impact, together with a slow, resonant interaction between the young planet and the migrating orbits of Jupiter and Saturn, could produce the tilt without the excessive spin. Nobody has yet found a model that reproduces every single detail of Uranus at once. But almost everyone agrees on the basic picture. Uranus, at some point deep in its youth, was hit. Perhaps once. Perhaps several times. Perhaps by objects that were themselves the last surviving cores of the icy giants that never finished forming. The Uranus we see today is the tilted, quieter descendant of that violence. And the strangeness of everything else about the planet, the offset magnetic field, the muted internal heat, the tilted rings, the tilted moons, the sideways year. All of it points back to the same distant moment, some 4.5 billion years ago, when something the size of the Earth arrived from the dark and struck. There is one detail from the Keck simulations that is, in a quiet way, one of the most beautiful facts in modern planetary science. If you strike a planet in the right way, you can make it lie on its side. But you cannot easily strike it back upright. Once a giant planet has been tipped past 90 degrees, its own moon system, its own gravity gradient, its own precession, all of them tend to hold the tilt where it is. Uranus will not right itself. It will sit on its side for as long as the solar system exists, which means that 97.77 degrees is, in a very slow, very persistent sense, permanent. Every summer at its North Pole, for the next several billion years, will be a summer of 21 continuous years of sunlight, on a world where sunlight is already very thin. Every winter, for the next several billion years, will be 21 continuous years of darkness. Whatever hit Uranus, hit it once. And Uranus has been carrying the memory of that impact, quietly, in silence, without weather that we can see, without warmth that we can measure, every single day since. If you could stand somewhere on the equator of Uranus and watch the sky over the course of a full Uranian year, you would see the sun perform a very strange arc. Near the equinox, when the equator is pointed toward the sun would rise and set in the ordinary way, tracing a normal daily arc from horizon to horizon and back again, every 17 hours. But approaching the solstice, that daily arc would tilt. The sun would rise not in the east and set in the west, but spiral instead across the sky. It would climb higher on one side and drop lower on the other. At the exact solstice, the daily motion of the sun would become nearly circular, a small, closed loop, high above the horizon in the sunlit hemisphere and completely absent from the shadowed one. An observer on the equator of Uranus at solstice would see the sun neither rise nor set for many months. They would see instead a small, bright disk circling the sky like a slow gnat, once every 17 hours, for as long as the season lasted. No landscape on any world we know of would look right by that light. The seasons of Uranus would not just feel unfamiliar, the very geometry of daylight would be alien, to the point that human intuition, built from a world tilted at only 23 degrees, would simply refuse to make sense of it. When Voyager 2 arrived in January 1986, that geometry was, for the first time, close enough for a spacecraft to see. And it is to those 5.5 hours that we will now, finally, turn. The final approach lasted for months. Voyager 2 had left Saturn in August of 1981 on a trajectory that had been carefully bent by Saturn's gravity to swing outward toward Uranus. For 4.5 years it coasted through empty space, further from the sun than any working spacecraft had ever been. At Saturn's distance, the sun is a very bright star. Beyond Saturn, it is a smaller, colder star. By the time Voyager 2 was approaching Uranus, sunlight was only about 1/370th of what falls on the Earth, roughly 0.25%. Everything on the spacecraft had to be adapted for the low light. The cameras were reprogrammed from the ground, sending updated instructions over a signal that took years to fully install. The exposure times were lengthened. The maneuvering routines were adjusted to compensate. The onboard computer, which, by modern standards, had less processing power than a pocket calculator, was reprogrammed remotely to squeeze more useful data out of every kilobit of transmission. The spacecraft itself was, by early 1986, aging. One of its 2 radios had failed within its first year of operation. Its scan platform, which pointed the cameras, had begun to stick during the Saturn flyby and had been carefully coaxed back to health. But the main systems were still working. The nuclear power source, 3 radioisotope thermoelectric generators fueled by plutonium-238, was still producing enough electricity to run the instruments and the radio. And the flight team at the Jet Propulsion Laboratory in Pasadena had rehearsed the Uranus encounter for years. Beginning in November of 1985, Voyager 2 entered its official Uranus observing period. The early images were, at first, disappointing. Uranus, in the first close approach photographs, looked more or less like it had looked from the Earth, a pale bluish-green disk, without visible bands or storms or any of the swirling weather that had made the Jupiter and Saturn images so famous. For weeks, the team looked at the images and looked at the images. Nothing was moving, nothing had features. There was some concern that the encounter might, in a scientific sense, not deliver much. The situation began to change in the middle of January 1986. Voyager 2 was now close enough that its cameras could resolve small moons. Faint moving points began to appear near the planet, moons no one on Earth had ever seen. The imaging team began to count them. 1, 2, 3. By the 24th of January, they had spotted 10 new moons. An 11th, buried in the same set of images, would only be picked out from the archive years later and given the name Perdita. The dark rings, previously known only from ground-based occultations, began to appear directly in the images, thin arc-like lines against the darker background. And the magnetic field of Uranus, which no one had ever detected from Earth, began to make itself known. Voyager 2 carried, on the end of a long boom, a magnetometer. The boom held the instrument as far away from the main body of the spacecraft as possible, so that the spacecraft's own weak magnetic fields would not confuse the measurement. Beginning about a day before closest approach, the magnetometer began to record a signal that was clearly not from empty space. The magnetic field of Uranus was reaching out to touch the instrument. The Planetary radio astronomy experiment, which listened for radio waves in the range of about 1.3 to 1.5 megahertz, began to detect the faint hiss of trapped particles rotating in the field. Uranus, it turned out, has a magnetosphere. And its magnetosphere is unusual in ways we did not yet appreciate. The moment of closest approach came at 17 hours, 59 minutes, and 47 seconds Universal Time on the 24th of January, 1986. Voyager 2 passed within 81,500 kilometers of the cloud tops of Uranus, about 50,640 miles. For perspective, that is about a fifth of the distance between the Earth and the Moon. At that moment, the spacecraft was moving at about 19.4 kilometers per second relative to the planet, around 43,500 miles per hour. The whole close encounter phase, in which the target was large enough to fill a significant fraction of the camera's field of view, lasted a little more than 5.5 hours. Then, quietly and without fanfare, Voyager 2 began to slip past the planet on the other side. The images and data continued to arrive, more and more slowly, for another 5 weeks. But the intense central passage, the moment when the spacecraft was truly close to Uranus, was over in less than an evening. The signal from that passage took 2 hours and 40 minutes to reach the Earth. The people watching the first close images of Uranus in the mission control room at JPL were watching photographs of a place that had, by the time they saw them, already been left behind. The Deep Space Network dishes that received the signal had been carefully coordinated. The 70-meter antennas at Goldstone in the Mojave Desert, at Canberra in Australia, and at Madrid in Spain each took their turn as the Earth's rotation carried them into and out of view of the receding spacecraft. For the crucial hours around closest approach, the antennas at Canberra were the primary receivers, and their measurements were relayed to Pasadena in near real time. At Pasadena, the raw images were displayed on monitors as they arrived. At first, the images of Uranus itself continued to show the same nearly featureless disk. Then something else came into view. Voyager 2 had been carefully timed to fly past a small, close-in moon called Miranda at nearly the same moment as its closest approach to Uranus itself. At about 29,000 kilometers from Miranda's surface, closer to the Moon than the Earth is to the Moon divided by 13, Voyager 2 turned its cameras and captured a set of images that even now, 40 years later, are still the only close-up photographs ever taken of that world. Miranda is a very small moon. Its diameter is only 472 kilometers, smaller than most European countries. It has a very low gravity, a very cold surface, and a face that looks, at first glance, as if it has been stitched together from 3 or 4 different worlds. We will spend most of a later part of this film on Miranda. For now, it is enough to say that its photographs, arriving at JPL that January night, were the surprise of the encounter. Nothing else Voyager 2 saw at Uranus looked like Miranda. Behind Miranda, still on its close-in trajectory, Voyager 2 also captured images of the 11 inner moons and the 11 then-known rings. The rings, when photographed in forward scattered light, that is, with the sun behind them, appeared much brighter than they did in reflected light. This is because the ring particles are very small, and they scatter light in the forward direction the way dust scatters the light from headlights on a foggy night. That single image, of Uranus and its rings backlit by the distant sun, gave scientists their first direct look at the tiny dust particles that fill the gaps between the main rings. Meanwhile, the spacecraft's radio, at a wavelength of about 13 centimeters, continued transmitting toward the Earth. At a precise, planned moment, Voyager 2 passed behind Uranus, from the Earth's point of view, an occultation. As the radio signal grazed the edges of the atmosphere, it was slightly bent by the density and temperature of the gas. Careful measurement of that bending, back at Goldstone, allowed scientists to construct a vertical profile of the Uranian atmosphere, from the very upper layers down to the depths at which the signal was absorbed. The same technique had been used at Jupiter and Saturn. At Uranus, it gave scientists the first direct measurement of the pressure and temperature structure of the atmosphere, a set of numbers that has not yet been meaningfully improved upon. Then Voyager 2 came out from behind the planet. The signal returned, and the encounter, in every practical sense, was over. 4 days later, on the 28th of January 1986, the Space Shuttle Challenger lifted off from Kennedy Space Center in Florida, carrying 7 astronauts, including a schoolteacher named Krista McAuliffe. 73 seconds later, at an altitude of about 15 kilometers, the shuttle's external tank ruptured. The shuttle disintegrated. Everyone aboard was killed. The news dominated American television and newspapers for weeks. The Uranus encounter, which had been the intended NASA news story for that same week, was pushed almost entirely off the front pages. Behind the scenes, at JPL, the work continued. The images kept coming down. Papers were written for the journal Science. Diagrams were drawn. Ephemerides for the new moons and rings were calculated and published. The magnetosphere was mapped. The ring particles were counted. The features on Miranda were named. But when the papers appeared, the wider world barely noticed. For most people, the Uranus flyby of Voyager 2 arrived and departed almost invisibly. It has never fully recovered its share of attention. Books about the outer planets are still, 40 years later, thinner on the Uranus chapter than on any other. And yet, the science was extraordinary. In one afternoon, Voyager 2 had increased the number of known moons of Uranus from 5 to 16. It had increased the number of known rings from 9 to 11. It had confirmed the presence of a magnetic field of a kind that no other planet in the solar system has. It had returned the first, and to this day, the only, close-up images of 5 of the largest moons: Miranda, Ariel, Umbriel, Titania, and Oberon. It had traced, at fine resolution, the vertical structure of an atmosphere that only telescopes had ever seen from far away. It had begun the study of the ring particles. It had detected a plasma torus. It had recorded the temperatures at the cloud tops of both hemispheres. It had timed the rotation of the interior of the planet via the pulsing of the magnetic field to about 17 hours and 14 minutes, a number that would only be refined by 28 seconds nearly 40 years later. And then, before anyone had really absorbed what had been seen, it was gone. The last close-in image of the encounter shows the planet Uranus, viewed from behind, receding. A small crescent of blue lit by the distant sun, with the great tilted circle of the ring system barely visible. Above the crescent, empty space. Below it, also empty. Voyager 2, in the moment that photograph was taken, was already moving toward its next target, the 8th planet, Neptune, still 3.5 years away. Everything else about Uranus, to this day, we have had to build from Earth. From the top of Mauna Kea, from a small square window in low Earth orbit, from a telescope parked at a stable point almost 1 million miles away. Never again, not once in 4 decades, has a machine seen Uranus from close. That is the fact that hangs over everything else in this film. That is why we keep returning to that single night. That is why one January evening in 1986, in a plain, brightly lit room in Pasadena, still shapes almost every question we know how to ask about the 7th planet 40 years later. If you could stand somewhere in the empty space above Uranus, holding a small compass, and orient it very carefully toward the planet's magnetic north, the needle would not point where you expect. It would not point roughly along the axis around which the planet is spinning. It would point off to the side, at an angle of nearly 60 degrees from the rotation axis. The Earth's magnetic field is not perfectly aligned with the Earth's rotation axis either. At present, the magnetic North Pole is tilted about 11 degrees away from the geographic North Pole, drifting slowly across northern Canada from year to year. That 11-degree tilt is enough to make magnetic compasses noticeably wrong in the far north. On Uranus, that same misalignment is nearly 6 times greater, 58.5 degrees between the magnetic axis and the rotation axis. There is nothing else like it in the solar system. Neptune, our closest analog to Uranus, has a magnetic field tilted by about 47 degrees to its rotation axis. That is also very unusual. But Uranus is stranger still, and its magnetic axis, in addition to being tilted so severely, is not even centered on the planet. The dipole, the underlying magnetic bar magnet, if we can call it that, sits offset from the geometric center of Uranus by about 1/3 of the planet's radius. That is roughly 8,000 kilometers away from the middle. The Earth's magnetic dipole, by comparison, is offset from the Earth's center by only about 500 kilometers, less than 1/10 of one Earth radius. For most practical purposes, the Earth's magnetic field is symmetric about the Earth. The magnetic field of Uranus is not. The result is a magnetosphere, the region of space around the planet where the magnetic field dominates over the solar wind, that is shaped very unlike anything else we know. On Uranus, the magnetosphere is a lopsided, corkscrew-like structure. As the planet rotates on its axis once every 17 hours and 14 minutes, the magnetic field wobbles wildly. The magnetosphere twists and pulses. Its geometry with respect to the incoming solar wind changes drastically over the course of every Uranian day. This behavior has been called a switching magnetosphere. It opens and closes over and over, faster than any magnetosphere in the solar system. Charged particles trapped inside, mostly protons and helium ions, blown loose from the outer atmosphere, are alternately squeezed and released. Voyager 2, in its brief passage through this magnetosphere in 1986, spent only a few hours inside it. That is not enough time to see very much. But it was enough to detect the field, measure its rough strength, characterize its offset and tilt, and confirm that the radio emissions coming from Uranus, first hints of which had reached the Earth from Voyager 2's approach, really did come from a planet-scale magnetic field, pulsing in step with the planet's rotation. The radio emissions themselves fall in a band from about 1.3 to 1.5 megahertz. That is well below the range that ordinary radios pick up, But Voyager 2's planetary radio astronomy instrument was designed for exactly this task. It heard the pulse. It measured its period. And from that measurement came the first accurate value for the rotation of Uranus: 17 hours, 14 minutes, and 24 seconds. Because Uranus is a fluid planet, no solid surface to time against, you cannot simply watch a mark move across the face of it, as you can with Mars or with the Earth from orbit. The only reliable clock inside Uranus is the magnetic field itself, generated somewhere deep in the interior, pulsing with the rotation of that interior. The number that Voyager 2 measured in 1986 held as the standard for almost 4 decades. Then, in 2025, a team led by Laurent Lamy at the Paris Observatory, working with the Hubble Space Telescope, published a careful reanalysis of long-term observations of the Uranian aurorae. Their result refined the Voyager number by about 28 seconds. The best modern value for the rotation of Uranus, published in Nature Astronomy in 2025, is 17 hours, 14 minutes, and 52 seconds. That is a small correction, but it is the first meaningful improvement on the Voyager 2 rotation rate in almost 40 years. And it comes not from a new spacecraft, but from a careful modern look at old images from Hubble. Now, why is the magnetic field of Uranus so strange? Where is it coming from? On Earth, the magnetic field is generated in the outer core. The Earth has a hot, molten, mostly iron outer core, thousands of kilometers thick, spinning inside the mantle. The motion of the electrically conducting iron produces electric currents, and those currents produce the magnetic field. The whole process is called a dynamo. Because the outer core sits, symmetrically, at the center of the Earth, the magnetic field it generates is also roughly symmetric about the center of the Earth. That is why the Earth's magnetic field is only mildly tilted and only mildly offset. Jupiter and Saturn have similar geometries, though the details of their dynamos are different. Both of them have their currents concentrated deep in their interiors, roughly symmetric to their rotation. Both of them have magnetic fields that are only mildly tilted from their rotation axes, 3 degrees for Jupiter, less than 1 degree for Saturn. Uranus does not fit that pattern at all, and Neptune does not fit either. Both of the ice giants have magnetic fields that are tilted at large angles, and both have fields that are offset from the geometric center of the planet. For a long time, the leading explanation involved the ice mantle we discussed earlier, the vast layer of compressed water, ammonia, and methane that makes up most of the mass of each planet. The suggestion was that, at the enormous pressures inside these worlds, part of the ice mantle was electrically conducting, and that the dynamo generating the magnetic field lived not in the deep core, but in a shell within that mantle, much closer to the surface and much less symmetric about the rotation axis. For a long time, that was speculation. It has, over the past decade, moved somewhat closer to being a fact. The key was the laboratory work on superionic water, which we discussed in a previous part of this film. Once physicists had shown that water, at the pressures and temperatures inside Uranus, really does enter a phase in which mobile hydrogen ions swim through a lattice of oxygens, the picture of a Uranian dynamo living inside that phase became much more plausible. If a shell of superionic water surrounds the deep core of Uranus, and that shell is convecting, that is, slowly circulating due to internal heat gradients, the moving ionic charges will generate electric currents. Those currents will generate a magnetic field. Because the shell is much closer to the surface than a deep core dynamo would be, and because the shell need not be perfectly symmetric to the rotation of the planet, the resulting field can be strongly tilted and offset, exactly the behavior that we see. Similar reasoning applies to Neptune. The two ice giants may share this same basic mechanism, hidden inside their mantles, generating in each case a magnetosphere that behaves in ways that no simpler dynamo could produce. We cannot yet prove this in detail, Voyager 2 did not carry the instruments necessary to map the field in fine enough resolution to distinguish between different dynamo geometries. Ground-based measurements from the Earth cannot detect Uranus's field at all. It is too weak at that distance to be picked up. Nearly every serious modern paper on the Uranian magnetosphere concludes with some version of the same sentence. We need to send another spacecraft. We need to orbit Uranus. We need to measure the field at many points around the planet over a full rotation, and preferably over more than one. We need instruments designed specifically for the kind of tilted, offset field that Uranus has. And of course, we do not yet have such a mission there. The Uranus Orbiter and Probe, which we will discuss in the last part of this film, is being designed with exactly this measurement in mind. If it flies, it will carry a magnetometer far more sensitive than Voyager 2's, and it will spend years in orbit around the planet, rather than a few hours passing through. For now, everything we know about the magnetosphere of Uranus we know from those few hours in January 1986, plus a great deal of very careful theoretical modeling. There is one more thing worth pausing on. The magnetic field of Uranus and the magnetic field of Neptune are the two most tilted planetary fields in the solar system. Every other magnetic planet in our system has a field that is fairly close to its rotation axis. But when we look more and more at planets around other stars, exoplanets, we are finding that ice giants like Uranus and Neptune, in the mass range of roughly 10 to 20 Earth masses, appear to be very common. Perhaps the most common kind of planet in the galaxy. Not gas giants like Jupiter, not small rocky worlds like Mars, not super-Earths. Ice giants. If Uranus and Neptune are anywhere close to being representative of that class, then the strange, tilted, off-center magnetic fields that we see around our own two ice giants may be a common feature of a very large number of planets across the galaxy, which would mean that Uranus, from our perspective, is not merely an oddity in the corner of the solar system. Uranus is our nearest example of the most common kind of planet there is. The next spacecraft that is sent to Uranus, when it eventually arrives, probably sometime in the middle years of this century, will not just be measuring one planet. It will be measuring, in effect, a class. Every dynamo model that spends a decade in orbit around Uranus and matches the observations will, at the same time, be teaching us something about the interiors of thousands of exoplanets we can never dream of visiting. The magnetic field of Uranus does not belong to Uranus alone. It belongs, in the deep sense, to a whole family of worlds. We just happen to have the nearest example. During that brief pass, Voyager 2's plasma instruments also detected something that had never been seen at any other planet. A ring of trapped hydrogen protons and helium nuclei orbiting Uranus at high energies, held in place by the tilted magnetic field. The trapped particles form a torus, a donut-shaped cloud, invisible in ordinary light, but easily detected by charged particle sensors, that co-rotates with the wobbling magnetosphere. Because the magnetic field is tilted so severely, the plasma torus is also tilted. As the planet rotates once every 17 hours, the torus swings up and down relative to the equatorial plane, alternately dipping into and out of the ring system, alternately intersecting and missing the orbits of the innermost moons. Some of the small inner moons of Uranus, then, spend part of every rotation of the planet inside a slowly cycling bath of charged particles, and part of every rotation outside it. The radiation environment on the surface of those moons is not steady. It comes in slow, 17-hour pulses. Nothing else in the solar system does exactly this. The next mission that arrives will spend years mapping how, and how strongly, and with what consequences for the surface chemistry of those small moons. For now, we know only that the pulsing is real, and that it has been going on for at least 4 billion years. And on one January afternoon in 1986, we came close enough to it to notice how strange it really was. Everything else we still have to do. Uranus has, at the last careful count, 28 known moons. Most of them are small, most of them are dark. Most of them orbit close to the planet, in the plane of its tipped-over equator, in the same direction that Uranus itself rotates. The largest known moon is only about 1,577 kilometers across, a little more than a third the diameter of the Earth's moon. There is no giant moon of Uranus, no world in the class of Ganymede or Titan. There are, instead, 5 moons that stand out from all the others by their size. They are called, in order of increasing distance from the planet, Miranda, Ariel, Umbriel, Titania, and Oberon. These 5 moons carry more than 99% of all the mass in the Uranian moon system. Everything else is small, dim, and mostly the aftermath of ancient impacts. The names of the Uranian moons all come, uniquely in the solar system, from English literature. Every other moon in the solar system is named after a figure from Greek or Roman mythology. For Uranus, John Herschel, the son of William Herschel, the discoverer of the planet, proposed in 1852 that the moons should instead take their names from the plays of William Shakespeare and the poetry of Alexander Pope. That tradition has held ever since. Titania is a character from A Midsummer Night's Dream. Oberon is her husband from the same play. Umbriel and Ariel are spirits from Alexander Pope's poem The Rape of the Lock. Miranda is a character from The Tempest. The smaller moons, Puck, Portia, Juliet, Belinda, Cressida, Desdemona, Bianca, Cordelia, Ophelia, Rosalind, Perdita, all come in the same way from the plays. Let us take the 5 large moons one at a time. Titania is the largest. Its diameter is 1,577 kilometers. Its mass is a little more than 3,500 million tons. William Herschel found it on the 11th of January, 1787, 6 years after he had found Uranus itself. He also found Oberon on the same night, using a larger 20-inch telescope he had built at his new observing site near Windsor. Titania and Oberon were the first 2 Uranian moons to be discovered, and they remained the only known Uranian moons for more than 60 years. Titania's surface, when Voyager 2 photographed it from about 360,000 kilometers away, showed craters, canyons, and long linear fault-like features that suggested some past internal activity. Some of those canyons are more than 1,500 kilometers long and up to 5 kilometers deep. Oberon is only slightly smaller, 1,523 kilometers across. Its surface is heavily cratered, dark, and, so far as Voyager 2's brief look could tell, largely inactive. The largest impact crater on Oberon, called Hamlet, is about 200 kilometers wide, with a bright peak at its center. Both Titania and Oberon appear to be made of roughly equal parts ice and rock, differentiated internally like small versions of the outer planets themselves. Both would, in principle, be interesting places for a future landing mission: cold, quiet, exposed to hard radiation, but geologically stable. Neither has been visited again since 1986. Umbriel is the 3rd largest, 1,170 kilometers across. It is the darkest of the 5 large moons of Uranus. Its bond albedo, the fraction of sunlight it reflects back into space, is only about 10%. 90% of the light that falls on it is absorbed. By solar system standards, this is very dark indeed. The reason is not fully understood. The dominant theory is that Umbriel is coated by a thin layer of ancient carbon-rich material, possibly formed in place, possibly delivered from outside, that has been slowly darkened over billions of years by exposure to charged particles from the Uranian magnetosphere. At the top of Umbriel, in one bright crater about 130 kilometers wide, called Wunda, there is a strange ring of high albedo material. It stands out against the surrounding darkness like a bright coin against a black cloth. We do not know what it is made of. We do not know how it got there. The images we have are just detailed enough to raise the question, and just poor enough to not answer it. Ariel is the 4th largest, 1,158 kilometers across. Ariel is also, by some measures, the brightest of the 5 large moons. Its bond albedo is about 23%, more than twice that of Umbriel. Ariel's surface, as photographed by Voyager 2, is one of the youngest surfaces we have found in the outer solar system. It is crossed by long, deep, straight-walled valleys that are hundreds of kilometers long. Some of them are flat-floored, as if something once flowed through them and froze in place. Ariel appears to have been resurfaced, at least in patches, sometime after most of the other Uranian moons finished forming. There is some evidence, from careful analysis of the crater counts, that this resurfacing may have happened as recently as 1 billion years ago. That is very recent, on the timescale of the outer solar system. Ariel and Umbriel were discovered together on the 24th of October, 1851, by the English astronomer William Lassell from a private observatory outside Liverpool. Lassell was a wealthy brewer and amateur astronomer, and one of the finest telescope makers of his generation. He had already, in 1846, discovered Neptune's moon Triton, only 17 days after Neptune itself was found. Ariel and Umbriel added 2 more to his catalogue. Between them, William Herschel and William Lassell, a musician and a brewer, found 4 of the 5 major moons of Uranus, without ever knowing what those moons were made of, or what they would look like from close. The 5th moon of the group had to wait almost another century. Miranda was discovered on the 16th of February, 1948, by the Dutch-born American astronomer Gerard Kuiper, the same Kuiper for whom the Kuiper belt of icy bodies beyond Neptune is named. Kuiper found Miranda on a photographic plate taken with the 82-inch telescope at McDonald Observatory in western Texas. By that time, the telescopes and photographic technology of the 20th century could reach objects that Herschel could never have imagined. Miranda is the smallest of the 5 large Uranian moons. Its diameter is only 472 kilometers. Its surface area is roughly the size of the country of Turkey. It is small enough that, if you were standing on it, you would be very close to weightless. The surface gravity on Miranda is only about 0.07 of a meter per second squared, less than 1/100th of what you feel on the Earth. A grown adult jumping straight up on Miranda would rise about 100 meters into the sky, hang there for many seconds, and come down slowly. A pebble thrown horizontally could travel for many kilometers before falling. And on Miranda, there is a cliff. That cliff is called Verona Rupes. It runs along the edge of one of the great fault systems on the moon's surface. It was photographed by Voyager 2 from close range in a series of images taken during the flyby. Its vertical drop, from top to bottom, is around 20 kilometers. That is by far the tallest known cliff in the entire solar system. 20 kilometers is more than twice the height of Mount Everest above sea level. It is more than 3 times the depth of the Marianas Trench. If you were standing at the top of Verona Rupes on Miranda and you stepped off the edge, you would not fall like you do on the Earth. Miranda's gravity is so weak that your descent would be slow. You would fall for something like 12 minutes before you reached the bottom. You would have time, in that fall, to see the wall of the cliff rising above you in the dim, distant sunlight, minute after minute, from a viewpoint that no living thing has ever occupied. At the bottom, you would land. Because there is no air on Miranda, there is no terminal velocity, and you would continue to accelerate as you fell, at a speed of about 56 meters per second. That is about 200 kilometers per hour, roughly 125 miles per hour. Fast enough to be certainly fatal, but slow enough that, in principle, a well-designed retro-rocket could bring you to rest before you struck the ground. There is no atmosphere on Miranda to slow you passively. Parachutes would be useless, so any soft landing would have to be done actively by burning fuel. The cliff is the tallest reasonable freefall in the solar system. Not the deepest canyon, not the tallest mountain. A cliff. One single, uninterrupted drop. 20 kilometers. Nothing on Earth compares. And the rest of Miranda is only slightly less strange. Voyager 2 photographed on Miranda 3 enormous, roughly rectangular features called coronae. They are called Arden, Elsinore, and Inverness, after locations in Shakespeare's plays. Each corona is hundreds of kilometers across. Each has a raised interior of concentric ridges and grooves surrounded by a smoother outer plane. They look, in the Voyager images, as if huge blocks of the moon's crust had been lifted up and dropped back down at slightly different heights, or as if slow-moving material from underneath had pushed up and refrozen at the surface. We do not know exactly how they formed. One hypothesis, popular in the years immediately after Voyager 2, was that Miranda had once been shattered by a giant impact and reassembled from the pieces, with the coronae marking places where the pieces had not quite fit back together in the same order. A more recent hypothesis, favored by many modern models, is that Miranda's interior went through slow convective heating and cooling cycles early in its history, and that the coronae are the places where that convection reached the surface. Both hypotheses require heat inside Miranda that, at the moon's very small size, is difficult to sustain over long times. One possible source of that heat is tidal flexing, the small, repeated deformation caused by Miranda's orbit through Uranus's gravitational field. If, in the past, Miranda had been in a resonance with one of the other moons, Ariel perhaps, the tidal heating would have been much stronger than it is today, and could have driven the internal processes that made the coronae. That resonance is long since broken, but the coronae remain. And that is the picture of the 5 large moons of Uranus. 2 ancient discoveries by an amateur astronomer with a home-built telescope. 2 discoveries 70 years later by a wealthy brewer with a private observatory. 1 discovery in the middle of the 20th century by a research astronomer at a large ground-based telescope. And then, in 1986, 1 afternoon of close-up photographs, and nothing since. Miranda, Ariel, Umbriel, Titania, and Oberon are still, in every practical sense, worlds that we have visited once. The Uranus Orbiter and Probe, when it flies, is planned to fly close by several of these moons more than once. If those flybys happen, they will be, for those 5 worlds, the second visit in the history of the human species. We have been waiting, at the time of this recording, for 40 years. We are going to have to wait a little longer. Uranus has rings. For almost 200 years after Herschel discovered the planet, nobody knew this. Saturn's rings had been known, more or less clearly, since the 17th century, a famous luminous system visible in even a modest telescope and one of the most photographed objects in astronomy. Jupiter's faint rings would not be found until Voyager 1 arrived at Jupiter in 1979. Neptune's rings would not be found until the same instruments that first found Uranus's rings, a decade later, were pointed at Neptune. But the story of the discovery of Uranus's rings starts, oddly, in the air. On the morning of the 10th of March, 1977, in the pre-dawn hours over the southern Indian Ocean, a Lockheed C-141 Starlifter cargo aircraft was flying at an altitude of about 12.5 kilometers. It had been modified, inside, into a flying observatory. The rear cargo bay had been fitted out with a 91-centimeter Cassegrain telescope mounted so that it looked out of a small square window in the port side of the fuselage. The aircraft was called the Kuiper Airborne Observatory, in honor of Gerard Kuiper, the same astronomer who had discovered Miranda, and for whom the Kuiper Belt would eventually be named. The aircraft was operated by NASA out of Moffett Field in California. That morning, the aircraft had flown out over the Indian Ocean to catch a very specific event. Uranus, moving slowly along its orbit around the Sun, was about to pass in front of a distant star from the point of view of the Earth. The star was called SAO 158687. It was a faint, unremarkable star in the constellation Libra, but for a few seconds, from the correct place on the Earth's surface, Uranus would slide directly in front of it. The star would disappear briefly behind the planet, and then, on the other side, it would reappear. The astronomers on board the Kuiper Airborne Observatory, James Elliott from Cornell University, along with Edward Dunham and Douglas Mink from the Massachusetts Institute of Technology, wanted to observe that occultation. Their goal was simple. By measuring exactly how the star faded and brightened as Uranus's atmosphere passed in front of it, they could determine the profile of the Uranian atmosphere far more precisely than any direct measurement had yet allowed. It was, at the time, cutting-edge remote sensing. The team turned on their photometer and began to record. The star was visible, the clock ticked, and then, several minutes before Uranus itself was due to occult the star briefly flickered. Then it flickered again, and again. 5 separate brief dips in the star's brightness, one after another, all before Uranus had arrived at the star. Then Uranus itself moved across the star, blocking it entirely for the expected number of minutes. Then, on the other side, the star reappeared. And, several minutes after Uranus had left the star flickered 5 more times. 5 dips before the planet, symmetric with 5 dips after the planet. Something had been blocking the star's light before Uranus even arrived. Something, in space, close to the planet, but not the planet itself. Elliott, Dunham, and Mink recognized, almost immediately, what they had found. Uranus had rings. They were narrow, thin, dark rings, not the vast, bright disk of Saturn, but they were rings, 5 of them, symmetric around the planet. They wrote up their observations and published them within weeks in Nature. In the years afterward, ground-based observations of other Uranian occultations found more rings. By the time Voyager 2 arrived at Uranus in January 1986, at least 9 narrow rings had been catalogued from the ground. The names of the original 5 rings from the discovery paper are letters of the Greek alphabet: Alpha, Beta, Gamma, Delta, and Epsilon. Later editions received their own letters, a few more Greek letters, and then a few numerical designations. The complete list, today, has 13 named rings. Voyager 2 photographed all of them in 1986 and discovered 2 additional ones during its flyby. The rings of Uranus are unlike any other planetary rings we have seen. They are, above all, dark. The individual ring particles have a bond albedo of roughly 2%. 2% of the light that falls on them is reflected. 98% is absorbed. For comparison, the ring particles of Saturn, the great bright ring system that Galileo saw in 1610, have bond albedos of roughly 60 to 80%. They are almost pure water ice. The ring particles of Uranus are as dark as charcoal. We do not know exactly what they are made of. The favored explanation is that they are ice, mostly water ice, that has been chemically darkened over billions of years by exposure to the harsh, charged particle environment of the Uranian magnetosphere. Organic compounds, long carbon molecules formed by radiation processing of methane and other simple molecules, accumulate on the surface of the ice grains and slowly turn them black. A similar process seems to darken the surfaces of Umbriel and of many of the small icy bodies further out in the solar system. The individual ring particles themselves are not fine dust. They are, on average, based on the way they scatter light in different directions, roughly the size of walnuts and boulders. There is very little dust between them. That is different from Saturn's rings, which contain a broad mix of particle sizes from grains up to house-sized chunks, and different from Jupiter's rings, which are almost entirely fine dust. The narrowness of the Uranian rings is one of their most distinctive properties. The Epsilon ring, the outermost and brightest of the original 9, is about 100 kilometers wide. Most of the others are much narrower. Some of them are less than 10 kilometers across. At a distance of many tens of thousands of kilometers from the planet, a 10-kilometer wide ring is essentially a line. There is nothing in nature that naturally produces such narrow rings. Left to themselves, ring particles will spread out over time. Collisions between the particles and the gravitational tug of small moons will smear a narrow ring into a broader one within a few million years. Yet the Uranian rings persist, in their thin lines, for what appear to be billions of years. Something must be holding them in place. That something is a set of small moons. Voyager 2, on its way past Uranus, photographed several tiny moons orbiting immediately inside and outside the Epsilon ring. Two of them, Cordelia, orbiting just inside the ring, and Ophelia, orbiting just outside, are almost exactly where a phenomenon called shepherding would place them. A shepherd moon exerts a gravitational tug on ring particles that try to drift outside its orbit. Cordelia pushes any inward drifting particles back outward. Ophelia pushes any outward drifting particles back inward. Between them, the two moons maintain the boundaries of the Epsilon ring. Similar mechanisms probably operate elsewhere in the ring system, though we have not yet directly identified the shepherds for every ring. Some of them may be small enough that Voyager 2 missed them entirely. Some of them may have shattered long ago, leaving only the ring itself behind. One of the possibilities that a future orbiter would be able to test. There is a small, quiet fact about the Uranian rings that is worth pausing on. Because the equator of Uranus is tipped over almost 90 degrees, the entire ring system is also tipped over. From the point of view of an observer approaching Uranus from the Sun, the rings can appear anywhere from edge-on to fully face-on, depending on the moment in the Uranian year. At the equinox, the moment when the Uranian equator is pointed toward the Sun, and thus toward the Earth, the rings are seen edge-on. They effectively disappear from view. At solstice, they are seen face-on, and they are as bright as they will ever be. Voyager 2 arrived at Uranus at almost exactly solstice. The rings, at that moment, were fully face-on to the spacecraft. If Voyager 2 had arrived 7 years earlier or later, at equinox, it would have seen a very different geometry, one in which the ring system was almost invisible from most angles, and the moons crossed the visible face of the planet twice per orbit. Uranus, in its normal Earth-based observations, presents different ring geometries every few years, cycling slowly through the 84-year seasonal cycle. For a long time, our best images of the Uranian rings were still the Voyager 2 images. The Hubble Space Telescope, launched in 1990, could resolve the ring system, but only in favorable geometries. In the last few years, however, the picture has changed. In April of 2023, the James Webb Space Telescope, a large infrared observatory, positioned about 1.5 million kilometers from the Earth on the far side from the Sun, pointed its near-infrared camera at Uranus. The results were remarkable. For the first time, the rings of Uranus were photographed in the infrared with extraordinary sharpness. The images clearly showed all 11 of the main narrow rings. They also showed, more clearly than ever before, a broad, diffuse inner ring called the Zeta Ring that had been hinted at in Voyager 2 data but never fully imaged. The Zeta Ring appears as a soft glow inside the innermost of the narrow rings, a wide, hazy sheet of very fine material orbiting closer to the planet than anything else in the system. Additional James Webb images released in 2024 went further. They showed atmospheric features on the planet itself in an intensity of detail that had been unavailable from any earlier telescope, and they mapped the seasonal changes in the northern polar cap of the planet as it slowly turned toward the Sun. We will return to those seasonal changes in the next part of this film. For now, the important point is that the rings of Uranus, 40 years after Voyager 2 first photographed them, are only just beginning to reveal themselves. The Kuiper Airborne Observatory, on which they were first discovered, was retired in 1995. Its telescope was later placed on display at the Moffett Field Historical Society Museum in California. The seat that James Elliott occupied on the morning of the 10th of March, 1977, is now behind glass. The rings themselves, the very thin, very dark lines of material that lie tipped over around the seventh planet, are still there. They are still holding their positions. They are still, quietly, in the same place they have been for perhaps 1 billion years. And they are, still, some of the most exotic ring systems in the solar system, waiting for a spacecraft to come back and, this time, look at them for more than a single afternoon. The Epsilon ring, in particular, has one feature that has puzzled scientists ever since Voyager 2 first saw it up close. It is not a perfect circle. Its outer edge is slightly further from Uranus at one point in its orbit than at the opposite point, a difference of about 800 kilometers, on a ring whose radius is roughly 51,000 kilometers. Its width also varies with position, from about 20 kilometers at the narrowest point to about 100 kilometers at the widest. The two shepherding moons, Cordelia and Ophelia, appear to be maintaining not just the ring's boundaries, but its whole eccentric shape. Detailed models of exactly how this works, the resonances between the moons and the ring, the tiny gravitational tugs, the collisions between particles, are ongoing. Nobody has yet reproduced the exact geometry of the epsilon ring in a simulation that starts from first principles. The Uranian rings are, in that sense, one of the most detailed test problems in celestial mechanics that we currently possess. They are a small, well-defined, elegantly bounded natural experiment, sitting at the edge of the solar system, in which the fine-grained physics of ring dynamics can be studied in almost complete isolation from everything else. We just, right now, cannot get close to them. For the 20 years after Voyager 2 left Uranus, the planet was mostly a disappointment. Every telescope big enough to resolve it showed the same thing: a small, pale, blue-green disk, a little brighter at the pole that happened to be tilted toward the sun. No visible bands, no visible storms, no visible weather at all. Uranus, in every image from every Earth-based observatory during the 1980s and 1990s, looked essentially like it had looked to Voyager 2, a featureless world. For a while, some scientists began to suggest that this might really be the case, that Uranus, unlike its noisy neighbor Neptune, was fundamentally a quiet planet, with almost no internal heat to drive convection, and therefore almost no visible weather. That view was wrong. But it was hard to see why it was wrong until the geometry changed. The geometry of Uranus is unusual, as we have already discussed. Because the planet's axis is tipped over by almost 90 degrees, the seasons unfold in an extreme way. For a very long stretch of time, of order 21 Earth years, one pole is aimed almost directly at the sun. Then, over the next 21 years, that pole slowly turns away, and the equator swings around into the sunlight. Then, for the next 42 years, the geometry runs in reverse. This produces a pattern of extreme solstices and, in between them, 4 brief windows of equinox. At solstice, only one hemisphere is lit. At equinox, both hemispheres are lit, and the sun rises and sets across the sky on any point on the planet's surface in something approaching a normal day-night cycle. Voyager 2, as we said, arrived at Uranus almost exactly at solstice. The southern pole was pointed at the sun. The northern hemisphere had been in darkness for decades. The atmosphere of the sunlit southern hemisphere had, over the course of that long summer, settled into a strange, quiescent state. Almost no convection, almost no visible bands, almost no storms. The atmosphere of the shadowed northern hemisphere, meanwhile, was invisible in reflected light and could not be studied at all. Neither hemisphere was showing weather. For most of the ensuing 2 decades, the geometry did not change enough to matter. The southern pole was still tilted toward the sun, the northern hemisphere was still hidden in shadow, the atmosphere was still quiet. Then, slowly, over the course of the 1990s and the early 2000s, Uranus began to swing. The pole that had faced the sun began to turn away. The equator began to swing into the sunlight. The northern hemisphere, which had been dark for 4 decades, began to emerge into the light. And Uranus, over those years, began to change. The first hints came from the Hubble Space Telescope, which had been launched in 1990 and, by the mid-1990s, was returning much sharper images of Uranus than had ever been possible from the ground. Faint atmospheric bands began to appear. Faint storms, small, bright cloud features, drifting eastward and westward at various latitudes, began to show up in the deepest exposures. At the same time, a new generation of ground-based telescopes was coming online. The Keck Observatory on the summit of Mauna Kea in Hawaii had been equipped with a system called adaptive optics, a device that uses a rapidly deforming mirror to cancel out most of the blurring effect of the Earth's atmosphere in real time, allowing a 10-meter telescope on the ground to produce images almost as sharp as those from a space telescope. When the Keck telescope, using its adaptive optics, was pointed at Uranus in the early 2000s, it began to see structures that had been invisible before. Bright bands of cloud in the northern hemisphere, small storms drifting in the flow. By 2006, the storms were large enough to be given names. The most prominent of them was called the Dark Spot 2, a dark, oval feature in the northern hemisphere, similar in appearance to the great dark spot that Voyager 2 had seen on Neptune. By 2007, Uranus reached equinox. The 7th of December 2007 is the moment when the Sun crossed the plane of the Uranian equator from north to south. For a brief period, both hemispheres of Uranus were lit equally. Both hemispheres were, at last, available to telescopes on the Earth, and Uranus, in the images taken during and after that equinox, was, for the first time, unmistakably a planet with weather. The Keck observations, published by a group led by Heidi Hammel of the Space Science Institute and Imke de Pater of the University of California at Berkeley, showed a system of alternating light and dark bands running along many latitudes. They showed storms, small bright cloud features, moving with the wind and being sheared apart by it. They showed a general circulation pattern that, though slower than Neptune's, was clearly present. Perhaps most strikingly, the observations showed a large concentration of small bright cloud features in the northern hemisphere, the hemisphere that had been dark for so many decades and was now, finally, being warmed by the sun again. The atmosphere, it turned out, had been changing all along. It had simply been changing in a hemisphere that we could not see. Over the years since 2007, Uranus has stayed active. In 2014, a system of unusually bright storms appeared in the northern hemisphere, so intense that they could be seen from ground-based telescopes even without adaptive optics. They were reported by an international team including Larry Sromovsky at the University of Wisconsin and Imke de Pater at Berkeley. Some individual features in that outburst were tracked with wind speeds approaching 900 kilometers per hour, over 500 miles per hour, placing them among the fastest measured wind speeds anywhere in the solar system. For a planet that had been called, only a few years earlier, the most boring planet in the solar system, this was a considerable readjustment. The best current understanding is that Uranus's atmosphere is not truly quiet. It is only occasionally visible. The internal heat that drives its weather is small, but it is not zero. And the extreme geometry of the planet means that each hemisphere, in turn, spends decades in darkness, during which whatever weather occurs is invisible to us, and then decades in sunlight, during which telescopes on the Earth can watch what happens. By the 2020s, the James Webb Space Telescope had arrived on the scene. James Webb was launched on Christmas Day 2021 on an Ariane 5 rocket from French Guiana. It reached its parking orbit around the second Lagrange point, about 1.5 million kilometers from the Earth, in early 2022. Its near-infrared camera, called NIRCam, is exceptionally sensitive to infrared wavelengths. Uranus, and its clouds, and its rings, reflect and emit in the infrared in ways that reveal their composition and altitude in fine detail. The first James Webb image of Uranus was released to the public on the 6th of April 2023. It showed, at long last, all 11 of the main narrow rings in exquisite sharpness, along with the broad inner zeta ring. It showed a bright polar cap on the sunward hemisphere, and it showed subtle color variations in the clouds. A follow-up image, released in 2024, went further, resolving individual moon systems, showing a striking, bright polar collar around the North Pole and hinting at seasonal changes as the planet moves through its long spring. The changes are, by our timescales, slow. Northern Hemisphere spring on Uranus began around the equinox of 2007. It will continue until the Northern Hemisphere reaches summer solstice in about the year 2028. Between 2007 and 2028, telescopes on the Earth and in orbit have been able to watch uninterrupted the entire spring of the Northern Hemisphere of Uranus. That is an experiment that we have never been able to do at Uranus before, and will not be able to do again until the 22nd century. We are, in a small but real sense, watching one Uranian spring. It is the first Uranian spring that the human species has ever seen. Nobody, in the entire history of astronomy, watched the previous one. Nobody was watching the one before that. Uranus was found in 1781. Its northern hemisphere entered spring around 1965. But in 1965, no ground-based telescope had the resolution to see any weather on Uranus at all. The Keck adaptive optics system did not exist. Hubble did not exist. James Webb did not exist. Nobody watched. The next Uranian northern spring will begin around the year 2091. We do not know what humans, if any, will still be pointing telescopes at Uranus in 2091. Whatever picture they take will be a repeat of what we are seeing now, separated by an entire lifetime and by the entire scale of the planet's own year. For now, we watch. The polar cap brightens. The bands drift. The storms come and go. The rings, in every image, still lie flat around the equator of the tipped-over planet. And, at the poles, the seasons keep going in the same way they have gone for 4.5 billion years. There is one more thing. The change we are seeing at Uranus, from 2007 onward, is not just visible in images. The planet's spectroscopic signature, the pattern of colors reflected by its atmosphere at very small wavelengths, has been slowly shifting. The methane content near the poles appears to be changing with the seasons, as different air masses are transported around the planet. The stratospheric temperature, measured in the infrared, has been drifting. The planet is not just static behind slightly different lighting. It is, in a subtle but real way, responding to the season. Uranus, quietly, without ever making the front pages, has been doing weather all along. We had simply never been in the right place at the right time with the right instruments to see it. We are in the right place now. We should keep watching for as long as we can, because in about the year 2050, the northern hemisphere of Uranus will turn away from the sun again, and the whole cycle will begin its long descent back into darkness. And that will be, more or less, the moment when the next spacecraft finally arrives. There is a parallel worth mentioning. In 1989, 3 years after Voyager 2 left Uranus, it arrived at Neptune. There, on the same kind of blue world, it photographed an enormous storm, a dark oval as large as the Earth moving through the southern hemisphere. That storm was named the Great Dark Spot. 5 years later, in 1994, when the Hubble Space Telescope pointed at Neptune, the Great Dark Spot was gone. It had dissipated, in the intervening years, without any visible warning. In its place were new, smaller dark spots at new latitudes. The atmospheres of the ice giants, it turns out, are all like this. Individual storms come and go over decades. Bright polar caps appear and fade with the seasons. Bands rearrange themselves. Nothing on Uranus and nothing on Neptune is permanent. If we point James Webb at Uranus every year for the next 20 years, we will see a different planet in every image. That, more than anything else, is the argument for keeping the telescopes pointed there. Not because we expect to solve any single mystery, but because the seventh planet, like the eighth, is a moving picture, and we have, at the time of this recording, only seen a few thousand still frames from a film that has been running for 4.5 billion years. Every 10 years in the United States, the National Academies of Sciences, Engineering, and Medicine convene a very large committee of planetary scientists. The committee spends nearly 3 years reading, discussing, taking testimony, and eventually deciding. Its job is to write a document that sets the priorities for planetary exploration for the coming decade. That document is called the Planetary Science and Astrobiology Decadal Survey. There have been 3 of them, spaced 10 years apart. Every American planetary mission of the past 2 decades, every rover, every orbiter, every landed probe, has, in some sense, been chosen with reference to the recommendations of one of these surveys. The most recent one was published in April of 2022. Its full title is Origins, Worlds, and Life, a Decadal Strategy for Planetary Science and Astrobiology for 2023 to 2032. It is more than 700 pages long. Deep inside it, in the section on flagship missions, the largest, most expensive class of NASA planetary spacecraft, the committee named its #1 recommendation for the coming decade. The recommendation was a mission called the Uranus Orbiter and Probe. For the first time since Voyager 2 left the Uranus system in early 1986, the planetary science community of the United States had formally and unambiguously stated, "This is the most important mission we can send. We should send it now, or as close to now as we can manage." The Uranus Orbiter and Probe, as it is currently designed, would be a very large spacecraft. Its total launch mass, including fuel, would be a little over 7,000 kilograms. Its dry mass, the spacecraft itself, after the fuel is burned, would be around 2,700 kilograms. It would be powered by 3 plutonium-238 radioisotope thermoelectric generators, the same kind of nuclear power source that Voyager 2 has been using for the past 47 years, and that the Cassini spacecraft used at Saturn, and that the Curiosity rover is using on Mars right now. Plutonium-238 is not weapons material. It is a heat source. As it undergoes radioactive decay, it emits alpha particles and heat. The heat is converted into electricity by thermoelectric couples. For missions to the outer solar system, where sunlight is too weak to power solar panels of any reasonable size, Plutonium-238 is essentially the only source of electricity we know how to build. The United States and Russia together produce very small quantities of it. The available stockpile is one of the practical constraints on how many outer solar system missions can fly. The Uranus Orbiter and Probe would consume enough Plutonium-238 that its production would have to be planned years in advance. If everything goes well, the spacecraft would be launched sometime in the early 2030s. The exact launch date matters because Uranus is a moving target. To get to it efficiently, a spacecraft needs a gravitational assist from Jupiter. The favorable launch windows for a Jupiter-assisted trajectory to Uranus open, roughly, once every dozen years or so. The current best-known windows fall in the years around 2031 and 2032. If those windows are missed, the next practical opportunity would come in the late 2030s or early 2040s. If the mission launches in 2032 and takes advantage of the Jupiter assist and coasts across the outer solar system for roughly a dozen years, it would arrive at Uranus around 2044 or 2045. That is roughly 60 years after Voyager 2's flyby. When it arrives, the spacecraft would carry out a challenging maneuver, a long propulsive burn to slow itself down enough to be captured into orbit around Uranus. Voyager 2 did not do this. Voyager 2 simply flew past. That was, in fact, the point of Voyager 2. It was a flyby mission from the beginning, without the fuel or the design to stop anywhere. The Uranus Orbiter and Probe would carry the additional fuel and the additional design mass needed to enter orbit and then to stay in orbit for years. The current mission concept calls for a science mission of about 4.5 years in Uranian orbit. During that time, the spacecraft would swing through carefully chosen paths around the planet, using flybys of the large moons to reshape its orbit, sample different regions of the magnetosphere, look at the rings from different angles, and probe the atmosphere at many different latitudes and longitudes. Somewhere near the beginning of the mission, probably shortly after orbital insertion, the spacecraft would release a small entry probe. The probe would separate from the orbiter, adjust its trajectory to hit the atmosphere at the right angle, and plunge into the top of the Uranian clouds. For a few tens of minutes, it would transmit back measurements of the pressure, temperature, and composition of the gas as it descended. Then it would burn up. The Galileo mission, which arrived at Jupiter in 1995, did exactly this, dropped a small probe into Jupiter's atmosphere, and returned measurements to about 22 atmospheres of pressure before contact was lost. For Uranus, the atmospheric probe would provide, for the first time, direct chemical composition measurements from inside the planet's atmosphere. We would finally learn, in detail, the ratio of noble gases inside Uranus. We would learn how the abundance of heavy elements, carbon, nitrogen, oxygen, really compares to that in Jupiter, in Saturn, in Neptune, and in the young Sun. We would test, in a way that no telescope from the Earth can, the various competing models of how Uranus formed and evolved. The orbiter, meanwhile, would carry a suite of remote sensing instruments, much better than Voyager 2's, though based on principles Voyager 2 also used. There would be a magnetometer, more sensitive than Voyager 2's, sampling the strange, tilted, offset magnetic field of Uranus over a full range of geometries. There would be an ultraviolet spectrometer, an infrared spectrometer, a wide-angle camera, and a narrow-angle camera, together capable of returning images of the planet and its moons in exquisite detail. There would probably be a radar instrument, a synthetic aperture radar, that could, at close range, look through the atmospheres of the airless moons and reveal, at last, the subsurface layers of Miranda, of Ariel, of Umbriel, of Titania, and of Oberon. We would learn whether any of those moons has a subsurface liquid water ocean, a question that, today, we cannot answer. The best guess, based on the meager Voyager 2 data plus theoretical modeling, is that Ariel and possibly Miranda might have thin subsurface oceans, kept liquid by very small tidal heating from their orbits around Uranus. The Uranus Orbiter and Probe could give us a definite answer, one way or the other, for each of the 5 large moons. The estimated cost of the mission is not fully settled. Recent internal studies have placed the price tag somewhere in the range of 4 to 6 billion United States dollars, spread out over the many years of construction and operation. This is comparable to what the Cassini mission at Saturn cost. It is comparable to what the current Europa Clipper mission, launched in 2024, will cost. It is a large amount of money. It is not, by the standards of major national programs, an unattainable amount of money. The Decadal Survey Committee, in choosing Uranus as its #1 flagship for the coming decade, weighed all of this. They looked at Uranus. They looked at the alternatives, a possible Enceladus Orbilander, a possible dedicated Mars sample return mission, a possible Venus lander, a possible Pluto orbiter, and they chose Uranus. The reason is not because Uranus is more spectacular than any of those other places. The reason is because Uranus, uniquely among the 8 planets, has been visited only once, and only briefly, and only 40 years ago. Everything we know about the interior structure of an ice giant, the most common kind of planet in the galaxy, based on the exoplanet statistics, is built on that one flyby, plus decades of careful theoretical modeling. Everything we know about the strange magnetic field of an ice giant is built on the same thing. Everything we know about the interior heat budget, the composition, the ring dynamics, the moon histories, all of it is built on one visit. And in the 4 decades since that visit, our questions have only grown. The lab experiments on superionic water have opened entirely new questions about ice giant interiors. The James Webb observations have shown atmospheric structure that we did not know existed. The exoplanet surveys have made it clear that Uranus is not merely an oddity. It is the local example of a whole class of worlds that we cannot otherwise reach. The Uranus Orbiter and Probe is not, in a scientific sense, an ambitious mission. It is a long overdue mission. It is what we should have done if the priorities of the last 30 years had been different. If it launches on time, if it survives the long cruise, if it enters orbit successfully, if it operates as planned, then, around the year 2044 or 2045, human eyes will see close-up images of Uranus for the second time in history. The people who watched Voyager 2's images arrive at JPL in January 1986 were, in some cases, senior scientists and engineers who had spent decades preparing for that moment. Many of them are now retired. Many of them are no longer alive. The people who will watch the Uranus Orbiter and Probe's first images arrive at JPL at some undetermined date in the middle years of this century are, in many cases, still very young. Some of them, right now, are graduate students. Some of them are undergraduates. Some of them are still in school or have not yet been born. The engineers who will build the spacecraft, the scientists who will operate its instruments, the mission planners who will draw the trajectories through the moon system are, in a substantial fraction, people whose careers are still ahead of them. The Uranus Orbiter and Probe belongs to a generation that, right now, is only beginning to arrive. It is not our mission, it is theirs. And so we come back, one last time, to where we started. On the 24th of January 1986, at 1759 hours Universal Time, a small aluminum and graphite spacecraft, 825 kilograms in weight, passed within 81,500 kilometers of the cloud tops of a pale blue-green planet. Its cameras and instruments recorded, in 5.5 hours, everything we still know today about that planet from close up. Then, it kept going. Voyager 2 is still transmitting. It is more than 20 billion kilometers away. The signal takes nearly 19 hours to reach us. By the end of this decade, its instruments will fall silent, one by one, as its plutonium-238 slowly cools. Sometime around 2030, the last transmission will end. The spacecraft and its data will remain in the archives at JPL. The images it took of Uranus and its moons and rings will still be there. They will still be, at that point, the only close-up images we have. We will not have any new ones. Not for another decade or more. Not until the Uranus Orbiter and Probe, or whatever the mission ends up being called, finally arrives. If you look at Uranus in a telescope on a very dark night, from a very dark place on the Earth, you can just see it as a tiny bluish-green disk, a pinprick of pale color, at the very edge of what a good backyard telescope can resolve. It will look, in that telescope, more or less exactly the way it looked to William Herschel in 1781. Small, steady, faintly blue-green, not doing anything unusual. But you will know, standing at the eyepiece, that the tilted-over planet is turning on its side over its long, long year. That its magnetosphere is opening and closing every 17 hours. That its rings, 13 dark, narrow lines that you cannot possibly see, are still holding their positions. That its 5 large moons are still there, quietly circling the tilted equator. That, at the top of a cliff on the smallest of them, there is a 20-kilometer drop that no human has ever stood beside. And that all of this, the whole strange, tilted, slowly turning world, has been visited only once, one January night, 4 decades ago. We will go back. Not soon, but we will. Until then, we watch from very far away. And on that night, when the first new close-up images of Uranus finally arrive, After 6 decades of waiting, after 2 whole generations of astronomers who never got to see the planet from up close, someone will look at them and remember, quietly, that we have done this before. Once. And that a small spacecraft, still moving through the dark, still transmitting, still holding its instruments open to a sky that will eventually swallow it whole, is the reason we know how much there is left to see.